Good morning everybody, this is Marco Vallone from Politecnico di Torino and I'm presenting a modeling contribution in which Plasmonics is exploited to enhance the absorption efficiency in mercurium-cadmium telluride or Mercatel mid-wavelength infrared detectors. I will introduce the motivations behind this investigation and the simulation strategy. Then the general theory and the simulation results will be presented. In the end, some conclusions will be given. Our idea is to increase the detectivity, D star, of focal plane array detectors by enhancing the infrared light coupling efficiency in the Mercatel absorber layer. Just a quick reminder, the detectivity D star depends on the ratio between the responsivity, capital R, and the integral of the thermal generation rate on the detector volume. This is a very general schematics, just a couple of pixels of a planar focal plane array, where each pixel is substantially a reverse biased photodiode. Mercatel is a quasi-ideal material for such devices, except for the obvious fact that Auger and Shockley-Dole and subsequent carrier diffusion from quasi-neutral regions limit its quasi-ideal performance. Immediate remedies can be the adoption of barrier detectors or fully depleted dual-layer heterostructure. They have known drawbacks, but they are valid remedies. Whereas a not valid remedy is to reduce the absorber's thickness, because the responsivity would be reduced as well. However, we will come back on this point in a moment. To understand, let's focus on our starting point, the expressions of the responsivity and the detectivity, and consider an alternative approach to enhance the detector performance: periodic metallic nanostructures deposited on the detector's illuminated phase. They allow for the excitation of surface plasmon-polariton modes, I will show this, which will lead to a significant light absorption efficiency increase. Our strategy is the following. Let's suppose that these plasmonic modes significantly enhance the responsivity, capital R. If this would be true, we could reduce the absorber thickness. The responsivity will be reduced as well, we can say to its initial value. However, since the absorber is thinner, we expect a higher detectivity because the integral of the generation rate is done now on a reduced volume. Then we could end with a detector with a similar responsivity but higher detectivity. We will see that also the interpixel crosstalk will be considerably reduced. This is a subject that has been investigated in depth. There are a lot of recent contributions. I listed here only a few, but almost only from the electromagnetic point of view, whereas multiphysics, say electromagnetic plus transport simulations, are still a not so explored field. So let's start with our simulation strategy. Initially, we will consider only electromagnetic simulations and a simplified version of the pixels to show the mechanisms. We divide one of the pixels into columns. Let's call them unit cells. Now we add a sort of gold nanorod on its illuminated phase. It is clear that if we impose periodic boundary conditions along horizontal sides, with these illumination conditions, the unit cell describes not only the single pixel, but also the whole focal plane array. Okay, but the question is, why such plasmonic nanorods should enhance absorption? A standard calculation, I will give you later the references, shows that surface waves exist along the interface between a material of negative permittivity and one of positive permittivity, in this case gold and Mercatel. They are known as surface plasmon-polaritons, and this is the X wave vector expression. However, a direct illumination on a flat surface cannot excite these modes because energy and momentum conservation prevent this. In our case, the infinite repetition of unit cells constitutes a Bragg rating, which supplies the needed extra momentum, and the mode coupling becomes possible for some resonant wavelengths. As a consequence, the absorptions by Mercatel can be greatly enhanced at that wavelength. In summary, periodic nanorods array acts as an optical cavity which, for some resonant frequencies, confines the light inside the sub-wavelength volume. The surface plasmon-polariton is a stationary mode in this case. For who are interested, here there are some references on this point. We performed all the electromagnetic simulations by the commercial package RSoft by Synopsys, which solves the Maxwell's equation by the FDTD method. The illumination is a plane wave with wavelength between 2 and 5 microns, so in the mid-wavelength band. Here there is an example which shows the mechanism at play, obtained by illuminating the unit cell by a plane wave at 4 microns. In the two plots, we show the X component, the transversal component of the electric field, in units of the amplitude of the illuminating field. And they represent what happens without and with the nanorod. And for this component, nothing of particular takes place. The two plots are quite similar. Instead, and as expected, the Z component of the electric field is very different in the two cases. Without nanorod, the Z component of the electric field is absent because the mode remains a TE mode. On the contrary, with the nanorod, the Z component is quite large, and in the Mercatel it concentrates around the metal semiconductor interface. And this is the most important plot, the absorption rate per unit volume in the two cases. And we can notice that the absorption enhancement due to the plasmonic effects is very evident. And here we can see the effect of the so-called critical coupling discussed in the background theory section. We have defined the enhancement factor capital M as the ratio between the absorption integrated in the Mercatel with and without the nanorod. Around the cutoff wavelength, here, the first resonance takes place for grating period, capital lambda, a little smaller than 1.5 microns, and the enhancement factor strongly depends on the wavelength, resulting much stronger closer to the cutoff wavelength, where the material is more transparent. Consider now a complete pixel with passivation, electrical contact, and doped as N-on-P photodiode. It has been suggested that in the mid-wavelength band, the optimal choice for the pixel pitch is 3 microns. This is in order to operate in the diffraction limited regime. With this constraint, a good value for the grating period, capital lambda, is 1.5 microns, that is very close to the first Bragg resonance shown in the previous page. Therefore, we performed a series of spectral multiphysics simulations, that is electromagnetic FDTD, followed by electrical drift diffusion simulations obtained by the Centaurus device simulator. In the end, we obtained the responsivity and detectivity spectra. Here we have the responsivity on the left and the detectivity on the right for a standard non-plasmonic detector, 5 micron thick, and which is a very common choice. Here, with the black lines, we show what happens if we reduce the thickness to 1 micron only, still for non-plasmonic devices. As expected, the responsivity significantly decreases. But not the detectivity, because in its expression we reduce the capital R, the responsivity, but we also reduced the volume on which the integral is performed. And here the red lines show what happens if we add the nanorods to the illuminated face of the thinnest detector. On the left plot we see that we have almost recovered the responsivity of the thickest standard detector. Now shall we consider the right plot? The detectivity D star for the thinnest plasmonic detector, the red line, is the highest one. We have considerably increased it with respect to both the other two cases. So the outlined path is a good way to obtain high detectivity with very thin absorbers. Okay, but why do we need thin absorbers? Of course, because the reduced absorber volume makes the impact of the thermal generation rate to decrease. Therefore, it is possible that also the dark current benefits of this fact. But in addition, if we are able to obtain a high-performing detector with an absorber layer much thinner than usual, we may reduce the interpixel crosstalk due to lateral carrier spreading. One of the methods to investigate the interpixel crosstalk is to simulate the effect of a narrow Gaussian beam focused on the central pixel of the miniarray. The diffusive crosstalk is a measure of how many carriers are photogenerated in the central pixel but are collected by one of the neighboring pixels. Of course, if the detector is thin, this is less probable. In this plot we can see that a detector 1 micron thick is characterized by a diffusive crosstalk which is more than 1 order of magnitude lower than the corresponding value of a 5 microns thick absorber. We see also that the crosstalk is almost not affected by the plasmonic nanorods, but its presence is precisely what makes it possible to consider very thin detectors. And just to conclude, I collected here the 3 plots that summarize the simulation results. To put it in a nutshell, we showed a way to obtain much thinner detectors than usual by adopting plasmonic nanostructures on the detector illuminated face. This allows for a consistent reduction of the diffusive crosstalk, higher detectivity, without sacrificing responsivity. Thanks everybody for your attention.